And I think maybe I mentioned this last time. Usually I would have posted a module on Friday, but there'll be a new module that I'm going to post very soon, hopefully later today. But it'll be due after spring break. So that's part of the reason I wasn't in a hurry to post it, because we're going to lecture. All right. So last time, at the end, we just kind of introduced the idea of a prime number, which you've probably seen before, right? It's numbers that their only divisor is 1 and themselves. So, but today I want to continue exploring that, prove a few theorems about them, explore some interesting facts. So here is the first theorem. If n is composite, it has a prime divisor less than or equal to the square root of n. Let me just say something first before we prove this about kind of the practical implications of this. One very practical application is, if you have a number and you're trying to figure out if it's prime or not, if you're doing it just by kind of trying out some possible divisors and seeing whether they divide it, right? You can stop when you get to the square root of n. If you haven't found one by then you're definitely not going to find one if you keep looking, because this says if there is one, you're going to find it by the square root of n. It has some other practical applications, but that's kind of the biggest one. So for example, if you're testing a number less than 100 to see if it's prime, you only have to test if it's divisible by primes that are less than 10. Right? If it's not divisible by 2, 3, 5, or 7, then it's prime, because any number under 100, its square root is, at most 10. So you don't have to check if it's divisible by 11 or 13 or whatever. Let's prove this. And I also want to point out this statement actually is packing a lot in a few words. And if we write out like formally, kind of in propositional logic, what it means, you'll see there's actually a lot there. So formally, all right. So this is a statement about all n. So for all natural numbers n. Well, I'm not going to write out like a formal definition of what it means to be composite. We could do that, but for the purposes of this, I'll just say we have some predicate that says, if n is composite, right, then what? It has a prime divisor less than or equal to n. So that part is saying that some number exists, right? So this is an exist statement. It's saying there exists some number which is a prime divisor of n. And so it's an exists, right? There exists, we'll call it D. Right, and then what is it saying about D? It's actually saying 3 different things are true about D. And again, they're kind of all packed into a very short phrase. D has to be prime, it has to be a divisor of n, and it has to be less than or equal to the square root of n. So it's an and. So D is prime, and D divides n, and D is less than or equal to the square root of n. Or you could probably rewrite this in a slightly nicer way. You could say D squared is less than or equal to n. That's nicer because we don't have to talk about square roots. We can just talk about operations on natural numbers. Okay. So how do we prove this? Well, so let n be an arbitrary natural number. And suppose it is composite. This is just the normal way that I'm starting a proof of a for all, and then I'm just doing a direct proof to suppose it's composite, and then see if we can show that some number exists. So let's first, before we get on to proving this exists part, let's unpack a little bit what it means for n to be composite or composite. Honestly, I really don't know. I'm like just second guess myself if there's a correct way to pronounce that word, or if I've been saying it wrong my whole life, or it really is either way. I don't know. Maybe I'll look it up later. Because I was saying composite earlier, but I just caught myself saying composite, so I don't know. Whatever. So that is, what does it mean for a number to be not prime, composite? Well, it means it has some divisor that's not 1 or n, right? So there is some a which divides n. That is, n is equal to a times b, where a and b are neither 1 nor n. Right, so this n is equal to a times b, and a and b aren't 1 and n. Of course, n equals 1 times n, but that's true of any number, including primes. So since it's composite, it's equal to a times b, and they're not, they're between 1 and n. Okay? So now, we're trying to find, we're trying to prove this. We're trying to find some D that has all those properties. So A or B might be good candidates, right? Because A and B are, of course, divisors of n, so they already fulfill this property. But we don't particularly know whether, how big they are, and we also don't know if they're prime. So let's tackle this property next. And I claim that A and B can't both be bigger than the square root of n. So here's how I argue that. So if both A and B were greater than the square root of n, then their product would be greater than n. Right? If I have two things that are exactly equal to square root of n, and I multiply them, I get n. If I have two things that are bigger than square root of n, and I multiply them, I get something bigger than n. Right? But we know that their product is equal to n. N equals AB. So this can't be true, right? They can't both be bigger than square root of n, because their product would be too big. Right? But their product is equal to n, hence, at least one of them must be less than or equal to the square root of n. Actually, exactly one of them, because we could do the same argument to show that they can't both be less than square root of n. I guess they could both be exactly equal to square root of n, right? But if one's less, then it's going to be greater, but it doesn't matter. And here's a phrase that you hear in proofs sometimes we haven't really talked about. I'll write it down and then I'll say what it means. So, without loss of generality, suppose A is less than or equal to the square root of n. The without loss of generality means, so what I just said is at least one of A or B has to be less than or equal to the square root of n, and I don't know which it is, right? And so what lets me just say, well, let's say it's A, because it could have been B, right? I don't know. The point is, A and B, it doesn't really matter. It's just like two numbers that multiply to n. I could name them the opposite things if I wanted. It wouldn't really change anything. So I'm just saying, look, let's just say from the beginning that we happen to pick A to be the one that was less than or equal to the square root of n, and B is the one that's bigger. It doesn't really matter which one I call which, so I haven't lost anything by just saying, suppose this, right? Okay, well, we have this number A and remember, what we're trying to show is that there exists some number that has certain properties. Okay? Does A have all the required properties? What is not a yes? R is not a yes. Here is not a yes. Adam says yes. These are all wrong. Which properties does it have for sure? It divides n. Yes, agreed. That's what we said. We said there is some A which divides n. So it satisfies that property, check. Also now, we just spent the last couple sentences arguing why it's less than or equal to square root of n. So it has this property also, right? Is it prime? Shrug? I don't know. I mean, it might be, but we don't know that. Okay? So A doesn't yet, we can't quite yet say that A satisfies. Okay, so here's the thing. I mean, if A is prime, then great, we're done. Right? If A is not prime, then the fundamental theorem of arithmetic says, well, you can decompose A into a product of a bunch of primes. And then the claim is, any one of its prime divisors would actually have all the right properties. Because A's divisors divide A, which divides n, hence all the divisors divide n. All its divisors are smaller than it, so they're definitely also less than the square root of n, and they're prime. So if A is prime, it is the number we're looking for. Otherwise, by the fundamental, I'm going to write it out this time, but in general, in the future, I'm just going to write FTA, theorem of arithmetic. FTA. And you'll see that gets abbreviated all the time. If you ever see a math teacher talk about FTA, that's a different. Arithmetic, it can be written as a product of primes any one of which has the required properties. Since divisibility and less than or equal to are translated. questions about this? Okay. Here's an example application. This is the Sieve of Eratosthenes. Maybe you've seen this. I don't know, but this is an ancient Greek method of finding all the primes up to a certain limit. And is there any? I don't think there's any faster way for me to do this than just. So I'm just going to go over here. I don't know. We'll just do it to like. No, we can do it again. Just do it to like 36. So the point is, you write down a whole bunch of numbers, like all the numbers up to some limit. If you look in the PDF of the lecture notes, there's a picture of doing this process up to 100, but I don't want to write out all the numbers from 1 to 100 right now. For some reason. So we'll do it to 35. And, okay, well 0 and 1 are not prime, they're special, right? So you go along in 2, the first number is 2, so that's 2 is prime. What we're going to do now is we're going to cross out all the multiples of 2. Because now that I know that 2 is prime, anything that 2 is a divisor of is not prime. So, and the reason I wrote it kind of in a square is that it makes it easy to kind of look for patterns and cross out all the multiples of 2 at once, or multiples of things at once. So like actually, all the even numbers are just in like columns. Right? So I've now crossed out all the multiples of 2. And then I keep going, and I say, all right, what's the next number? 3. So 3 is not crossed out, so that means it is prime. Because if something is crossed out, it's not prime, and if I get to a number and it's not crossed out, it means that nothing before it was a divisor, so it must be prime. So 3 is a prime. And I'm going to now cross out all the multiples of 3, which I guess are like all of these ones. Also all of these ones, which I can cross, I can cross them out again if I wish. They're already crossed out, so it doesn't matter. And then, okay, 4 is the next number, but it's already crossed out. 5 is the next number, it's not crossed out, so it is prime. So I'm going to cross out all the multiples of 5, which I believe in this picture, so here's like 10, 15, so it goes like, this line goes down like this. Also 35. Okay, now, here's the thing. Here's the point. We went up to 36, right? The square root of 36 is 6. So that theorem we just proved tells us, I guess we went to 35, right? There's 36 numbers starting at 0. The square root of 36 is 6. So that means any number up to 36, if it has a divisor, the divisor has to be at most 6. Okay? 6 is not prime. Here it is. And so at this point, we can just say we're done. Right? Any other number which is not crossed out has to be prime. I don't have to keep going and be like, oh, 7, let me cross out all multiples of 7. 11, then let me cross out multiples of 11. I don't have to do that. I can just go ahead and say, all right, everything else that's not crossed out is prime. 7, 11, 13, 17, 19, 23, 29, 31. Okay. So this is actually a very efficient method for generating a list of all the prime numbers up to some limit. And it's actually a fun exercise to write a computer program to do this, right? You can make a big array, and you have a little loop that goes through, and each number, maybe you have an array of booleans, right? And you set them all to true to start. It's like, it might be prime. And every time you get to one that's still true, you you say, okay, that's definitely prime, and I'm going to go through, now I'm going to have a loop that goes through like by steps of, you know, whatever that number is, and cross out, like, set everything to false that I can do. And then you go to the next number, and you keep doing that, but you only go up to the square root of, you know, whatever number you're trying to find, and then you've got, and from that point on, right, any number you can just look up in the array and see is it prime or not. So that is it is an ancient application, but it is also actually relevant today. So if you have, you know, maybe up to like, you know, up to, let's say maybe up to 1 billion. If you just want to test numbers up to like 1 billion, it's actually reasonable to make a giant array, run this process, and once you've done that, it might take you a few minutes, but once you've done that, you've now got your lookup table, and you just know all the primes up to 1 billion. If you want to test numbers much bigger than that, there's other ways you can do it, but all right. Any questions about that? I don't know. Personally, I find it kind of soothing. Like if you're bored, sit there and write out a grid, you know, as big as you want, and just like find the prime numbers. All right. So here's another theorem. This is another ancient theorem, but it's nice to see the proof. There are infinitely many prime numbers. And you might already know this fact. This fact might seem intuitive to you, perhaps, if you've seen this before, but I just want to point out, like, there's not any a priori reason to believe that they should be infinite or not. Like, it's certainly, it seems possible that, you know, there's a set, you know, there's a fixed finite set of prime numbers, and just every number above that is compositing. You can just, like, you're combining them, and you're multiplying more and more of them to get bigger and bigger numbers, but after a certain point, the primes stop, and everything after that can be built out of, like, this set of primes. But it turns out that's not true. And they certainly, you know, even if you look at this picture, you can see that, like, even just looking at this, it seems like maybe they get rarer as we go on. Right? The first row had 3 of them, and then there's 2 on each row, and then the last 2 rows only have 1 each. Right? And that's true. They do get rarer and rarer as you go, but they never stop. So how do you actually prove that? So this is a classic proof by contradiction. And there's actually lots of ways to prove this. And it's sort of, in some ways, it's sort of a mathematical pastime to, like, use some, like, fancy overkill methods to prove that there's infinitely prime numbers. It's like, if you have some cool new advanced theory, you're like, well, here's how we can use it to prove that there's infinitely prime numbers. But, so proof by contradiction. So suppose, we're going to suppose the opposite of what we're trying to prove. Suppose there are only finitely many primes. We're going to give them some names. We'll call them P1, P2, P3, ... Pn. Okay, so there are exactly n prime numbers, and we're going to call them P1 through Pn. Here's what we're going to do. We're going to cleverly use them to build a new number and show that leads to a contradiction. So let Q equal P1 times P2 times P3 ... times Pn plus 1. So in other words, you take all the prime numbers, you multiply them all together, and you add 1. That's going to be a big number, potentially, but it's certainly, since there's only finitely many prime numbers, quote, quote, we can certainly do that. That'll give us some finite number. And I want to think about what primes Q might be divisible by. So notice that Q is equivalent equivalent mod P1. What is Q equivalent to mod P1? So, well, it's, so this number here is P1 times something, right? So that is equivalent to 0 mod P1, because it's a multiple of P1, right? It has no remainder. And then 1, of course, is just 1. So, does that make sense? Or in other words, right, Q is 1 more than the multiple of P1. That's obvious here because it's P1 times the big thing plus 1. Okay, but also Q is equivalent, Q is 1 more than a multiple of P2. Right, etc. That means, so Q is not divisible by any of the primes. Does that make sense? You'll see why Q cannot possibly be divisible by any of those prime numbers. Okay? But that can't be. The fundamental theorem of arithmetic tells us that every number can be written as a product of primes. Right? But by the fundamental theorem of arithmetic, Q must be divisible by some primes. Right? Either Q itself could be prime, or maybe there's some primes that, you know, you can write it as a product of some primes. But we assume that this was our list of all the primes in the world, and Q is not divisible by any of them. That's a conflict. So this little lightning symbol, sometimes people use to say contradiction. So, in fact, there are so many primes. Right. Another way to think of this proof is, you know, if you give me any finite set of primes, this is kind of a recipe for finding a new prime that's not on your list. You multiply them all and add 1. That thing you get might be prime itself, in which case, congratulations, you found a new prime. Or maybe it's not, but in any case, it has to be a product of some primes and all those primes aren't on your list. So you could factor that number Q, and you'll get some new primes that were not on the original list, right? So you can then throw those new primes in and, you know, do the same thing, and you'll find more primes. This is not a particularly efficient way to find primes, but it's just, in theory, you could do that forever, and you would keep finding more primes. Okay, so there's definitely no largest prime number, right? They keep going forever. However, this is just a fun aside, there is a particular number which is the largest prime that we currently know of. In other words, it's the largest number that we can point to specifically and say, this number we know is prime. We know there must be primes bigger than that, but we don't know specifically what they are. Okay, so let me tell you what that number is. I'm going to make a new page. So the largest prime, or I'll say the largest currently known prime is, and this has been the largest prime we've known about since, I think, 2018. So until someone finds a bigger one, this is the biggest one we know. 2 to the power of 8, 2, 5, 8, 9, 3, 3, minus 1. This is a very large number. If you write it in binary, it just consists of 82,589,933 ones. If you write it in base 10, it has about 25 million digits. So if you, I figured out some statistics here. If you printed it in a book, so let's say you had about 100 digits per line and 50 lines of digits per page, which is a pretty typical kind of thing for a book. It would require around 5,000 pages, so maybe like a 10-volume set on your shelf like this, just of this one number. Someone actually did that. There was a YouTube video where someone actually got it printed on some print-on-demand service, and they had like this giant set of books. It's like, here's this prime number. The reason it's of this form is because there are some special algorithms that are known for testing numbers of this special form to see if they're prime. It's way faster than any other number this size. So that's why the biggest number we know of that's prime. And there's actually something called the great, so this is called a Mersenne prime, a prime of the form 2 to some power minus 1. There's a project called the Great Internet Mersenne Prime Search, GIMPS, and they have some software you can download for free and run on your computer. So like when you're not using your computer, in the background it'll be running some software to check numbers like this to see if they're prime. So this biggest known prime number was discovered by some random guy who was running this on his computer, and cool. So, let's talk about divisibility tests. Again, this may be something that you've seen before, but maybe you haven't spent too much time thinking about why certain tests work, or how you might even come up with, or how people come up with them in the first place. So, for example, is 7431 prime? Anyone know?
I don't think it's prime.
You don't think it's prime?
It's divisible by 3.
It's divisible by 3. How do you know it's divisible by 3?
If I add the digits, the 15 and 15 is divisible
Right,
by
good. Yeah, exactly. So, probably many of you may also know that rule, that if you add up the digits of a number, you can kind of use that to tell you if it's divisible by 3, right? So, 7 plus 4 plus 3 plus 1 is 15. That's a multiple of 3, so the whole number is a multiple of 3. But I want to show you where that comes from. Okay. So no, because 7 plus 4 plus 3 plus 1 is 15, hence it is divisible by 3. Okay. But how do we know that? How do we know that works? So, how do we know this works? Right, well, why does that work? So here's the theorem. A number is divisible by 3 if and only if the sum of its digits in base 10 is divisible by 3. Okay, what's the proof? So you maybe knew that theorem, but how do we prove it? So let n be a positive integer. We're going to write n in its 10 to the k times dk. So dk is like the first digit of n in base 10. Right, that's the 10 to the k place, and then 10 to the k minus 1 times d k minus 1 plus 10 to the k minus 2 times d k minus 2 plus dot 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 plus, 10 times d1 plus d0. Okay, does that make sense? I'm saying this is how we write, when we write a number in base 10, this is what it means. Right? It means that I have a bunch of digits, and each digit is, is really being multiplied by some power of 10. Right? So it's like thousands, hundreds, tens. Okay. Well, note that 10 is equivalent modulo 3 to what? Divide 10 by 3, what do you get as a remainder? 1, right? Because since 10 is 3 times 3 plus 1. Right, and hence, if I have 10 to some power, well, raising something to a power just means multiplying a bunch of times, right? And we already know that equivalence modulo something is kind of compatible with multiplication. So if I have 10 times 10 times 10 times 10, modulo 3, that's the same as 1 times 1 times 1 times 1. So this is equivalent to 1 to the k, which is, of course, just 1. In other words, if I'm just adding and multiplying stuff, whenever I see a 10 to the k, modulo 3, I can just replace that with 1. And you could, if you want, you could try this to see. Like, 10 has a remainder of 1 when you divide by 3, but so does 100, right? 100 is 99 plus 1, so it's 1 more than multiple of 3. 1,000 is 1 more than 999. 999 is a multiple of 3. So n equals, 10 to the k dk plus dot 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 plus 10 to the d1 plus d0 is equivalent modulo 3 to, well, all those 10 to the k's all just go away because they're all just 1. So I'm just left with dk plus dk minus 1 plus dot 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 plus d1 plus d0. That's the sum of the digits, right? So in other words, this is saying that n and the sum of n's digits in base 10 have the same, are equivalent modulo 3. So they have the same remainder when you divide by 3. So that means that, if you want to know if n is divisible by 3, then if this sum is divisible by 3, it's the same. And this also shows, actually, this is useful for slightly more than just testing if n is divisible by 3. You can also use it to find the remainder when you divide n by 3. So even if I have a number that's not divisible by 3, if I add up its digits, then, and I find out that it's 1 more than multiple of 3, well then, the original n also was 1 more than multiple of 3. And of course, you can also chain this. So like, if you take some really big n and you add up the digits and you still get a pretty big number, you can just do this process again until you get a smaller number. So we could have even done it here, like in our example of 7431, you add up the digits, you get 15. You could add those digits again and get 1 plus 5 is 6. And then you're like, okay, 6 for sure is a multiple of 3. Okay. So this also shows why, let's think about if we did the same thing for 2 instead of 3. So if we're thinking about the remainder modulo 2, 10 modulo 2 is equivalent to 0, right? Because 10 is a multiple of 2. So when I do this same process for 2, all the 10s actually, 10 to the k's turn into 0, and everything just goes away except the last digit. And that makes sense, right? You can tell whether a number is even just by looking at the last digit. And the same for multiples of 5, right? 5 is all a divisor of 10. So all the powers of 10 go away, and you're just left with the last digit. So again, you just look at the last digit, tells you if it's a multiple of 5. How about 7? I'm just curious, does anyone actually know a divisibility test for 7? It's not commonly taught for some people. Dora, do you actually know one?
I heard one about what they the numbers like or something like that.
You might be thinking of, no, I've never heard anything like that for 7. Yeah, I don't know.
That's not actually a good idea.
Yeah, I don't know, I haven't heard that. There's multiple ones, and it's certainly possible there's other ways to test it that I don't know of, but, well, let's think about this. So, if I do kind of this approach, it doesn't really help that much, because 10 is equivalent to 3 modulo 7, and so, 10 to the k was equivalent to 3 to the k modulo 7, which, I don't know, that doesn't really help me simplify it all that much. But there's a different approach we can take. So, write n is equal to 10, we'll call it 10m plus d0. So I'm just going to split it into the last digit and everything else, right? So for example, if n is 7482, then m is 748, and d0 is 2. Okay, so just the last digit and everything else. And then I want to see if 10m plus d0 is equivalent modulo 7 to 0. Okay, and I want to see if I can kind of derive something else equivalent that will tell me whether that's true or not. I can, if I multiply both sides by minus 2, minus 2, why minus 2? Well, it's because I happen to notice that negative 20 is 1 off from a multiple of 7. And so that, in particular, it's equivalent to 1 modulo 7. So minus 20m minus 2d equivalent modulo 7 to 0. Right, this is definitely if, let me say, minus 20 is equivalent modulo 7 to 1. Right, because it's 1 more than negative 21, which is a multiple of 7. So this is m minus 2d. And this actually, this is kind of the basis for a rule that you can really do in practice. Right, what this is saying is, if you take a number and you kind of chop off the last digit and subtract twice the last digit from the rest of the digits, right, then that result is divisible by 7 if and only if the original thing was. So let's do an example. Or let me just say, so n, 7 divides n if and only if 7 divides how do I say this? The initial segment of n minus 2 times the last digit. So, as an example, is, do I have a number here? 7, 4, 5, 1, divisible by 7. divides 7451, if and only if, well, 7451, I'm going to subtract 2 times 1 from 745. So this is, if and only if 7 divides 745 minus 2 times 1, which is equal to 743. And that's if and only if. I can do this again, right? 743, I'm going to subtract 2 times 3 from 74. So this is 74 minus 2 times 3, which is equal to 68. And I guess I could do it one more time if I want. I mean, maybe at this point I could stop because I can see that 7 does not divide 68. I could do it one more time. I could say this is 6 minus 2 times 8, which is negative. That's okay. It's like negative 10. 6 minus 16. All right, negative 10 is for sure not divisible by 7. Right. So, no. Okay, but if we do an example where, let's see, if I do 7441, we'll just do 7441 leads to 744 minus 2 times 1, which is 742. And then that leads to 74 minus 2 times 2, which is 70. And check, right? 70 is divisible by 7. So, therefore, so is 744. So, I mean, you can, it's definitely possible to get good at doing this rule in your head so that it's easier than just like doing long division by 7. Whether you care about that, I don't know, but, right, and because of what we know before, checking 2, 3, 5, and 7 is enough to know whether any number less than 100 is prime. So, you can look at any number up to 100. Checking if it's divisible by 2 or 5 is easy. 3 is pretty easy. You just add up the digits and see if that's divisible by 3, and then you can use this to check if it's divisible by 7. So for a two-digit number, it's pretty quick. You just do, so let's say like 89. I say, well, 8 minus 2 times 9 is 8 minus 18, that's negative 10. That's not a multiple of 7. 89 is definitely not even. It's definitely not a multiple of 5. 8 plus 9 is 17. That's not a multiple of 3, so it's a prime. On the other hand, let's say like 91. You'd say, well, 91 is not a multiple of 2. It's not a multiple of 5. 9 plus 1 is 10. It's not a multiple of 3. 9 minus 2 times 1, oh, that's 7. Okay, so it actually is divisible by 7. So 91 is not prime. It's actually 7 times 13. Okay, let's see. I guess I just wanted to say really quick, there's actually one key step missing from our proof, which is that we don't actually know that this is an if and only if. Because multiplying is okay, but to go the other direction we'd have to divide by -2, and we don't know if that's okay. It turns out it is okay, but we haven't chosen it yet, so we'll get around to that later. All right. Remember, no class on Wednesday. I'm going to be attending a virtual conference, so I will see you all on Friday.